Let's consider what happens as we approach 2 for the function 1 over x minus 2. I know the value doesn't exist. I claim the limit doesn't exist. And since we did an example like this, the reason the limit doesn't exist is because the left and the right pieces are different. What is the limit as we approach from the left? What is the limit as we approach from the right? You can do this graphically. You can do this kind of heuristically. There are lots of approaches to this. Yep.
From the left, it would be negative infinity, while from the right, it would be like positive infinity, because you can see here it's going upward.
We have that vertical asymptote there. As we come in from the left, we get more and more negative, going off to negative infinity. And as we go to the right, come in from the right, we're going off to positive infinity. So those are not the same, which is why this overall limit doesn't exist. Okay. But there's another remarkable feature in this picture. When I look at the graph of 1 over x minus 2, near 2, I see that. What happens away from 2? Hold that thought, Leo. There's my negative infinity from the left, my positive infinity from the right. As I go to 2, I move away from 2. What's happening to my y values here?
Getting closer to 0.
If I use the phrase "they're getting closer to," then I want to think of that in a limit idea. So where am I going to that my y values are getting closer to 0? I'm going off to the right, or I'm going off to the left. And as I go in either of those directions, you're saying, hey, those y values are getting smaller and smaller and smaller and smaller, getting closer to 0. Well, that again, just as we said here, we're going down, as we come in from the left, we're going down more and more and more and more. If I say I'm going out more and more and more and more, then I can consider what x is doing as an infinite behavior. So I want to think about this direction and this direction as going to infinity. So I can actually change this idea and now say we can look at the limit as x grows without bound, as x goes towards infinity. And this is the positive infinity, so we're going off to the right. And I can also look at going to a negative infinity, getting more and more negative without bound, going off to the left. And in both of these cases, you're absolutely right, Gavin, that we are going towards 0. And I could build a table to justify that. I could also think kind of heuristically. Let me do a little hand waving here. As x gets gargantuan, huge off to the right, does subtracting 2 really make all that big of a difference? And 1 over some huge number is really, really tiny. 1 over a million, 0.000001. It's an itty bitty number. But million is small compared to how far out I could go. I could go out billions, trillions, quadrillions. I could go out to a Google 10 to the 100th power. 1 over that is almost undetectable by any modern means. Same thing if I went negative. 1 over a negative number is negative, but it's 1 over a negative large number is still really tiny. So both of these behave the same but I can't combine them because really we're going in two different directions. Infinity is an idea, not a number. So I'm not talking about the limit as we go to infinity and anything other than one limit there. I'm not talking about the limit as we go to minus infinity and anything other than one limit there. These don't get, it's not like a left and a right of the same number. It's a positive infinity and a negative infinity. They are two separate ideas. If I really want to be a pain in the ass, I could make an epsilon delta definition here. But my epsilon means I have to be close to zero, and then my delta says I have to be close to infinity? That doesn't make any freaking sense. So what we do is we change our definition formally to, instead of saying, oh, a limit at some small neighborhood around X, no, we're just going to say, oh, once you get bigger than a certain thing, you're inside that little bit. So instead of saying you have to be close enough, we say you have to be beyond a certain value. So anything bigger than whatever capital N is close enough. And again, this sort of belt around my limit will be the same idea. That illustration appears on page 134. But I'm really going to say the limit as x goes to infinity of a function is L if, whenever, x is arbitrarily large, f of x is close to L. And if I change that from x going to positive infinity to x going to minus infinity, I change the words arbitrarily large to arbitrarily small. Negative numbers are smaller than positive numbers. In our example, that limit is 0. There's a name for the line. The x-axis here is playing. Our graph gets closer and closer and closer to this line without ever touching it. Because you're always going to have 1 over something. That's never equal to 0. What's the name of that line? Horizontal asymptote. That's for this example. If I have an arbitrary limit as we go to infinity, then I have an asymptote at that number. So we had limits with values infinity and values minus infinity at vertical asymptotes. That was the 2 in our example. But now a horizontal asymptote is the limit as we go to infinity or minus infinity. It turns out that a rational function can have at most one horizontal asymptote. What's a rational function again? Talked about this on Monday when we talked about continuity. Because we said rational functions were continuous at every point in their domain, and I defined what a rational function was on Monday. So it should be in your notes. What's a rational function? The key word in rational is ratio.
It can be divided evenly.
Careful. That word evenly isn't necessarily true, and not that it can be, but that it is. A rational function looks like P over Q, where P and Q are both polynomials. So it automatically is something that is divided when the top and the bottom are just polynomials. So something like this, or this. All of those are rational functions. Let me give you one more as well. Please note, this does not involve any sort of roots. This does not involve any sort of trig function, exponentials, logarithms, any of that crap. Only, the rule I've stated only applies to rational functions. These four functions, each one has at most one, which means whatever the limit is as we go to positive infinity is the same as the limit as we go to negative infinity. That line is the only asymptote. But it could have none. There's at most one. That means we could have zero as well. How do I know? For each of those four, whether or not it has one, and if so, what is it? Yes, sir.
You can simply just graph it.
I could, but as with my limits, I don't want to just depend on my technology. I'd like a more analytic method to figure that out. That would require a table, right? And that's effectively drawing the same as the picture. Again, I'd like something a little more analytic.
Not sure, but I think one of them is like if the powers are the same, you divide them. So you've got coefficients.
There's something about powers here. I like that idea. And I'm going to go back to our first example, and I'm going to try and generalize it. So let me think about a function that's really simple. Let's think about one over x to a power, where p is any positive number. As x gets bigger and bigger and bigger and bigger, what happens to that? I don't care if you're doing x squared, the square root of x, the x to the fifth, or x to the 0.1. As x is getting bigger, the bottom of this fraction is getting bigger, which means
The whole numbers are going to get smaller and get smaller and smaller.
and if it's getting smaller and smaller and it's still positive, it's getting closer and closer to zero. With that in mind, Dominic, I think I can follow through on your idea. There's something about powers. So what I'm going to do is I'm going to look at each of my expressions, find the highest power involved, and divide everything by it. Let's start with this first one. The highest power of x in this fraction anywhere is x squared. So I'm going to take each and everything and I'm going to divide by x squared. How do I justify that? How do I know that that's an allowed thing to do? What I'm really doing is I'm multiplying by 1. And as long as I multiply by 1, I'm not changing stuff. The answer is equal to what I started with. Now, I freely admit that's a weird-ass looking 1, but it's something over itself, so it is 1. So when I do the distributive rule here, this becomes x over x squared minus 1 over x squared. And then on the bottom, I have x squared over x squared plus 3 over x squared. And now I can simplify those. Wherever I have an x on top and on bottom, I can cancel. So I have 1 over x on the top and 1 over x squared on the top. And on the bottom, I have a 1, x squared over x squared. Now I'm going to do something sneaky with the 3 over x squared. The sneaky thing is I'm going to take the 3 out of the top and put it in front of that fraction. I'm going to write that as 3 times 1 over x squared. And now my limit law applies. I can do all the crap we were doing in section 2.3. I can say, oh, take the limit of the top and the limit of the bottom separately from one another. But the limit of the top is 2 things being subtracted, so take the limit of each one. The bottom is 2 things being added, take the limit of each one. Hey, there's a 3 in front, put it in front of that limit. So really, I end up with 4 individual limits. Now, I'm going to write this out, but really what it means is you're plugging in. So this is my only time I'm going to write this whole thing out. Now notice that each and every one of the terms in parentheses, something I know how to take the limit of. And on top, that's a 0. That's a 0. On the bottom, that's 3 times 0, which is still 0. But that's a 1, because that's the limit of a constant. This limit turned out to be 0. That's my horizontal asymptote. And if you were to graph this, you would actually see that approaching the axis. If you were to build a table, as we go off to infinity, we get smaller and smaller and smaller. But if we're doing it to the right, then we're also doing it to the left, because there is at most 1. Okay? So when am I going to get something else other than 0? Let me pull another one from our list of examples up here. What's the highest power of x? So we do exactly the same thing. We multiply by 1 over x squared on top and on bottom. We divide every term by x squared. Now I'm going to do the simplification right here. I'll have 3x squared over x squared. That's just a 3. I'll have minus x over x squared. That's minus 1 over x. I'll have minus 2 over x squared. Notice I put the 2 in front, so I could write it as 2 times 1 over x squared. That's not strictly necessary. I could leave it as 2 over x squared, but I only wrote my original rule up there for 1 over. Down here on the bottom, 5x squared over x squared gives me a 5, plus 4, 1 over x, plus 4, 1 over x squared. And what happens when I split it up? Take all these limits.
You should get 3/5.
Exactly. All 4 of these pieces become 0. The only thing that survives are the terms that had the highest power in them. Aha. Which means, really, if I want to think about a shortcut, I could say only the highest power terms matter. And they're tied, so 3x squared over 5x squared is 3/5. And I'm done. However, I would point out that in the case where I do not actually have a horizontal asymptote, this doesn't work as cleanly. So I cheated earlier and I picked this one. That does not have a horizontal asymptote. Why? Think about what happens with a large number. If what I just said is correct and only the highest power matters, that really looks like that. Well, x cubed over x simplifies to x squared, doesn't it? What happens is we go that way on x squared. That's a parabola. Because the power on top is bigger than the power on the bottom, technically, if I want to know what's going on here, I should divide. Because that's an improper fraction, like 9 over 4. 9 over 4 is 2 with something left over when you do the division, right? So really what I should do is I should actually divide this. Remember long division? Exactly, Lindsay. Oh, crap. I don't want to do this long division. But I'm going to do the first step, and I'm going to say, oh, x goes into x cubed, leaves an x squared, which I then subtract. So I get minus x squared. I bring down the minus. I can keep going, right? But the fact that I already know that this is x squared with stuff left over tells me what's going to happen as we go out to infinity is we're going to kind of look like x squared rather than a horizontal line. That's not a horizontal asymptote. So I can now make an overarching general claim whenever I am looking at a rational function. If the power on top is bigger than the power on the bottom, I don't have an asymptote. If they're tied, I do have an asymptote, and it's based on the coefficients. If the bottom power is bigger, then I'm going to get 0. So I'm going to write this out formally, which means I need to think of my rational function as polynomial over polynomial. If r of x equals a n x to the n, a n minus 1 x to the n minus 1, dot, 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 a 1 x plus a 0. And on the bottom, I'll use b's. And so since the powers might not be the same, I use the a to the x to the n on the top. I use an x to the m on the bottom. Those are just big, long number times power of x, number times power of x expressions. 1. If the power on top is bigger than the power on the bottom, r of x has no horizontal asymptote. 2. If the powers are equal, then y equals an over bn. How do I know they're both n's now? Because the two numbers are the same, and so I can replace the m with an n. Is the horizontal asymptote. 3. If the power on top is smaller than the power on bottom, then y equals 0 is my horizontal asymptote. Asymptotic behavior. Figuring out what's going on as we get larger and larger and larger is actually really important. And of all things, computer science algorithms. You have a program. This program takes a bunch of data and does something. Maybe it sorts your list. Maybe it searches your list. Maybe it takes your data and makes a picture from it. How long your program takes to run depends on the size of your data set and how complicated your procedure is, right? It turns out that if you want to sort a list, and you know that there are, 100 things in the list, it will take you roughly some number times 10,000 steps, which is 10,000 is 100 squared. So we say that that acts like something squared. Here's a simple problem. Simple. I would like you to plan a trip for me. I want to visit every one of the 48 state capitals in the continental United States, starting in Harrisburg. You need to plan a road trip. How many different ways can we do that? Because I want you to find the shortest road trip. Gas is expensive. I don't want to drive from Harrisburg to California to Maine to Florida. I'd rather do it in some sort of logical semblance. This sort of a problem is called a traveling salesman problem. Go from place to place to place to place as inexpensively as possible. The only known algorithm for finding this at the moment is to write out all possible trips and then sort them by cost. Remember, I am starting in Harrisburg, Pennsylvania. That means there are 47 other cities for me to visit, right? So there are 47 choices for my second city, and 46 choices for my third city, and 45 choices, and 44 choices, and so on and so on and so on. This sort of a descending multiplication is called a factorial. So I can actually calculate that by asking it to do the factorial for me. Math, probability, factorial. That is 2.5 followed by 58 zeros. I'll go you one better, Joy. That's older than the lifetime of the universe since the Big Bang in seconds. Since the start of the universe, when God said, "Let there be," has only been 10 to the 42 seconds. If I wrote out one list every second since the universe began, I wouldn't be 1% of the way done yet. Any method by which I can figure out how to improve this algorithm to lower the asymptote will make my life better. That comparison, that sort of computer thinking, is called algorithmic complexity. And it's covered in the SCS 341 algorithms analysis. It's covered in discrete math about this much. So those of you taking that course, you'll see it there in chapter 3. But it's based on this idea of doing a limit as we go to infinity. There are ways to compare algorithms that are nicer. By the way, there is a faster search method that instead of taking sort methods, instead of taking n squared operations, takes n times the logarithm of n operations, which is smaller. So that asymptote is better. That's called the heap sort or the merge sort. Again, algorithms you'll see for sorting things. We do that all the damn time. Excel does it every day. Sort alphabetically. How does it do it? It uses one of those two. Which means if I go to look and sort the database of students here on campus, we have roughly, I think it's 32,000 students in the SQL database, because we have all of them present and past since that database came in. I have to, 32,000 squared. 64, 128, 2, 6, 5, 12, 10, 24. That's 1024 with 6. That's a billion steps. Which is why when you get on GriffinGate and say, "Show me my advising worksheet," it takes a while to find it. Okay. Questions? I'd love to say this is useless shit. I'm never going to use it. But every computer scientist I work with uses this in some fashion. Because it can't leave well enough alone, here's this one. Problem. There's a square root in there. This is not a rational function. Rules I was just using don't apply because of that square root. Well, if I can't just look at it and make a generalized sweeping statement about it, I have to go back to the trick that we came up with. I have to divide by the highest power of x. But what is the highest power of x in this problem? I heard somebody say 2 and I heard somebody else say 1. Is it 1 or is it 2? I do see an x squared, but that x squared is under a square root, and that cuts it down to 1. That sneaky little square root is kicking back at me. So when I go to actually do the multiplying by 1, I want to multiply by 1 over x, because really the highest power is x to the first. And I'm okay with that. On the bottom, that's going to be easy. But on the top, I got to do some algebra. We will find, unfortunately, that algebra is endemic to this course. There is not a day where I will not do some sort of algebra because I want to do something in calculus. So, on the bottom, the bottom is easy. But on top, how do I put those together to make my life easier? We actually said it before we went any further in trying to figure out what this problem was. We said, hey, there's a square under a square root, and those cancel each other out. So what if we put the x here like it was x squared under a square root? Well, then I have 2 square roots involved, right? And I'm dividing them. So let me do the algebra that goes with that. So notice that fraction on the top has a square root on top and a square root on the bottom. That's just one big square root, isn't it? If I'm taking the square root of the top and the square root of the bottom separately, I could take the square root and regroup. And I could make that a single square root. Oh, I like it. What happens inside that square root now? What's that, John? I have 2 things divided by 1 thing, right? So I divide each of them. That becomes 2x squared over x squared. That's just a 2. But it also is 1 over x squared, which stays there. But now I'm actually really happy to see this, because what happens as we go off to infinity to 1 over x squared? What happens to 5 over x? It's 5 times 1 over x. I got a number. It worked. Not bad. Not bad. The algebra was kind of sucky. I agree. But once I got that trick up there with the square root of x squared, I was okay. Problem. A big problem, a little problem. This is what happens as we go to the right. This is not a rational function, which means I'm not guaranteed that what happens on the right is the same as what happens on the left. So if I want to know what's happening on the left, I got to do this again for minus infinity. Now that sounds like a huge problem. The only difference between what's going on here as we go to the right, what's going on to the left, is in this trick. So I say to myself exactly the same thing to start with. The highest power of x is x to the first. So I'm going to put 1 over x on top and 1 over x on the bottom. On the bottom, that's easy. But on the top, I need to know what to put in that set of parentheses. And my brain says, hey, you did this before, do it again. Write 1 over the square root of x squared. But that's not right. Why the hell not? Let's look at those two things. When you have 1 over x, and you're going this way, 1 over x is negative. That's positive. When you take the square root, you put the plus or minus on the outside. And we didn't. I want this thing to be negative to match that, which I know is negative. I have to put that extra minus sign out in front because I'm going to the left. Ah, shit. For the record, everything else that we did in the previous example is exactly the same in this one. So the only extra thing that's going to be dealing with here is an extra minus sign. And that minus sign is in front of a square root, not inside the square root. And I do the same division like I did here when I bring that together. What happens as x goes off to minus infinity? 1 over x squared and 5 over x. Both 0. 1 over giant number. 5 over giant number happens to be negative, but it's really tiny. I don't care if it's negative 0 or positive 0. That's still 0. So notice that what is happening on the left is different than what is happening on the right because I did not have a rational function. I had a function with a root in it. We've seen this before. Now, it may have been a while since you all did trig, but when we did the inverse tangent, that function has a different horizontal asymptote on the right than it does on the left. Even back in algebra class, think about the graph of e to the x. What's the graph of e to the x look like? Graph of e to the x looks like that. We have an asymptote only on one side. The limit on this side is infinity. So it is possible to have different things happen on each side. But notice that doesn't happen for rational functions. It only happens for quote unquote transcendental functions. Trig functions, root functions. Technically, root functions are not transcendental. I apologize. That's not right. Radical functions and exponentials, logarithms, same sort of deal. Infinity is a weird thing, and the algebra I need to do to address it works best multiplying and dividing. So there's a very nice example in the text that asks about this problem. And if I say to myself, you know, I could just take that subtraction, take the limit of the first thing minus the limit of the second thing. That would be infinity minus infinity. That doesn't make a damn bit of sense, does it? Lindsay? I'm sorry, I thought you were asking me a question. So I can't do this as infinity minus infinity. But what I could do is I could play the algebra trick we played with the square root and the number previously. I can multiply by 1. And I use the square root plus x. That turns what looks like a subtraction problem into a division problem. You should finish the algebra involved here. And if you can then take the limit, after you multiply out the top and simplify as much as you can, you should get 0. There's only about 3 more lines of algebra in here, but that should work out to be 0. Tomorrow is question and answer day. Sections 2.4, 2.5, and 2.6. We'll see you all then. I hope you have a wonderful rest of your day.